Hey everybody, let's take a practice test. Done this 6 times already. I think this one might be the best. Alright. Practice test. Chapter 7. Practice test. Chapter 7. Practice test. Practice test. Practice test. If you're having any trouble getting any of these problems right, think that I can help you. I think I might. Watch me work through these problems and try them yourself. Answer your questions, I'm trying to help. It's a good experience for everyone involved. Let's get these problems solved. Woo! All right. All right, let's go ahead and check out the Chapter 7 practice test. So I'm assuming you've read this problem. So let's look at the important parts here. So Mr. Goldman says that there's a 17.5% likelihood of getting a dollar bill with a mustache drawn on George Washington. And he says that doesn't make sense because if you had $100 bills, that means 17 and 1/2 of them would have a mustache. And that just doesn't make any sense. So first of all, we need to know that this is incorrect. Mr. Goldman's assumption here. 17.5 is a probability. So that means that what I mean by that is the probability describes the likelihood that the event, in this case having a mustache on George Washington, will happen. It just means that that's the chance that you're going to get a dollar that has a mustache. In fact, if you think about this as a fraction, we can think about this as the fraction 17.5 out of 100. And we know with probabilities that this doesn't mean that this number is exactly going to come up. It's only an estimation of the likelihood that it's going to happen. In this case, we're actually dealing with experimental probability, if you remember. And we know that we're dealing with experimental probability because we know that 17 Magazine couldn't have gotten every single dollar bill in the world and said that and counted how many had mustaches on them. So what they likely did is they probably took a sample and then use that sample to come up with their probability as a percentage. So we had an experimental probability here, and again, it describes the likelihood that the event will happen. It does not mean that exactly 17.5 out of 100 dollar bills will have a mustache on them. And you'd want to write your answer out a little more, but hopefully my explanation has helped a little bit. So, number 2. Write an algebraic equation to solve the following problem, and you can use the 5D process. I'm going to go ahead and just do the equation here. So it says that Superman saves 30 more than twice as many people as Batman. And then Aquaman saves 42 less people than Superman. If altogether they save 48 people, how many did each of them save? So I have 3 people involved here. I have Superman, Batman, and Aquaman. And since Superman was dependent on Batman, I'm going to go ahead and make Batman the X that I start with. If Batman saves X number of people, then Superman saves 30 more than twice as many. I know I need to start with twice as many, 2X, and I need to add 30 more. So that's how many Superman saves. Now Aquaman saves 42 less than Superman. So I'm going to start with Superman's number, 2X plus 30, and I'm going to take away 42 because it's 42 less people then. And now I have my 3 expressions that are going to make up my equation. So if it says all together, we know all together means we need to add them all up. And we know that all together they save 48 people. So I'm going to go ahead and I'm going to add up 2X plus 30 plus X plus 2X plus 30 minus 42. And that needs to all equal 48. Now, 2X plus X plus 2X is going to give me 5X. And 30 plus 30 gives me 60 minus 42 would leave me with 18. So now I'm at 5x plus 18 equals 48. I need to subtract 18 from both sides. And I get 5x, this is a 0 pair, equals 30. I'll now divide by 5 to create a giant 1 on this side. And I end up with x equals 6. So remember, Batman saves X number of people, so we know that's going to be 6. We can now figure out Superman by plugging in that 6 there. So 2 times 6 plus 30. 2 times 6 is 12. 12 plus 30 is going to leave me with 42. And I can do the same thing over here. So 2 times 6 plus 30 minus 42. 2 times 6 is 12. 12 plus 30 minus 42. 12 plus 30 is 42. And 42 minus 42 is 0. So Aquaman saved 0 people. It was probably an emergency that happened on land. Okay, number 3. If you want to increase the length of the side of a square by 30%, what fraction can be used as the multiplier to find the length of the new side? And we might want to draw a diagram to help. I'm going to go ahead and draw the diagram. So we draw a line here. This shows that would be 100% of the square. That's where we're starting from. And we want to increase the length of the side by 30%. So we know that when I go up here, this amount is going to be 30%. So if I started with 100% and I'm going up 30%, I'm going to add those two numbers. My new place is 130% of the original. That's great, but it asks for a fraction that can be used as the multiplier. So I know that 130% is out of 100 because it's a percentage. So I can actually think of this as 130 out of 100. And you could stay there. I'm going to go ahead and simplify it. So I'm going to divide both top and bottom by 10, which is going to give me 13 over 10. And I think that's a pretty nice fraction there. Box my answer. Okay, so moving on to number 4. If a pair of shoes is going to be discounted, so discounted means down, and 15%, what decimal can be used as the multiplier to find the new cost of the shoes? Again, I'll draw a diagram. Here's 0, here's 100%. In this case, I'm going down 15%. So my new number is going to change by 15%. That means I'm going to subtract. I can see it's 15% lower. That's going to put me right here at 85%. Again, 85% is a percent. So to find the decimal here, I need to divide by 100. So one way we do that is we take where the decimal is, we move it over twice to the left. So 0.85 would be a nice would be the decimal that we'd want to multiply with. All right, number 5. Rewrite the equation so it has only integer coefficients. You can see here we have some fractions in the denominators. I'm going to go ahead and zoom in a little bit because it is a little small. All right, so what we want here is a lowest common denominator, and I'm going to multiply everything by the LCD. So in this case, 7 and 2 both go into 14, but we have this 10 over here, so we need a bigger number than that. I'm thinking 70 is going to work pretty nicely. And I'm going to go ahead and I'm going to multiply both sides by 70. Now, one thing you want to be careful about here is make sure you multiply 70 by every single term that's in the equation. So 70 over 7x plus 70 over 2 equals 70x over 10 plus 70. Notice that I multiplied it by the 1 as well. I can now simplify these. So 7 goes into 70 10 times. 2 goes into 70 35 times. 10 goes into 70. This time it's going to be 7 times. I got a little hung up there. And then we still have the 70 over here. And that's it for that, because it just says rewrite the equation so it has only integer coefficients. Now we want to solve either one. I would argue that the new one is definitely a lot easier to solve than that original one. So we're going to go ahead and I'm going to rewrite it here. 10x plus 35 equals 7x plus 70. I'm going to go ahead and subtract 7x from both sides. And that gives me 3x plus 35 equals 70. I need the 30. Oh, I'm off the screen. Sorry. Apologize. So I subtracted 7x from both sides. And I went ahead and I just rewrote the equation here. So Now I'm going to go ahead and subtract 35 from both sides. That's a 0 pair. 3x equals 35. And we can go ahead and divide both sides by 3. So I'm just going to move over here. X equals 35 over 3 works. We can also think of this as 11 and 2/3. Either way. B is a pretty cool question. It says, "What will we get the same answer we did in part A if we solve the other equation that we didn't solve above?" So, yes, we would. Because we multiplied everything by the same number, we multiplied it all by 70. We didn't change the equation anyway. We multiplied all terms by 70, which does not change the solution because all terms changed by the same multiplier, we'll say. Okay, number 6. Chauncey rides his horse at an average speed of 18 miles per hour. If he has 1,000 miles to ride, how many hours will it take him? And then how many days is that? So we know that the equation we saw in class is distance equals rate times time. In this case, the distance we want to go is 1,000 miles. The rate is 18 miles per hour, and then the time we don't know yet. So we can go ahead and we can actually divide both sides by 18, and that's going to give me my time, which is 1,000 over 18. That comes out to 55.5 repeater, and these are hours now because we're miles per hour and we're going miles. So that is our number of hours, and it says how many days is that. We know that 55.5 repeater. If we take away 24 hours, which is 1 day, this would give me 31.5 repeater. And then we can actually, there's a whole other day there too, so we can actually take away another day. So at this point now, you can see we're going to have 0.5 repeaters still hanging out over here. That we would have 7.5 hours left. So it's 2 days and 7.5 repeater hours. Which I know that number's, oh geez, I went off the screen again. I'm sorry. There you go. You can see my work now. All I did was subtract 24. So 7.5 repeater hours. 0.5 repeater is a little weird. We can multiply that by 60 to figure out how many minutes that is, but we don't need to. So down to, and my iPad here does not want to sit straight, so I have to kind of move my paper around. Let's solve these two equations here. In both of these, I'm going to use the same strategy. I'm going to go ahead and just multiply by a common denominator. So in both cases, I'm just going to multiply the two. I'm going to multiply both sides by both denominators. So 9 and 2 are my two denominators. So I'm going to multiply both sides by 9 and 2. On this side, the 9s cancel out. The left side, the 9s cancel out. That leaves me with 2 times 7, which is 14. And on the other side, the 2's cancel out, and that leaves me with 9x. Now I can go ahead and just divide both sides by 9, and x equals 14 over 9. Over to b, same thing, except this time I have an x in the denominator, so I'm just going to multiply both sides by 27x. On the left, the x's cancel out. I have 27 times 10, which is 270. On the right, 27 and 27 cancel out, and that gives me 13x. Again, just divide both sides by 13, and x equals 270 over 13, which we can actually simplify, but I'm going to go ahead and just leave it like. Okay, a little jump there, I got interrupted. So, Rudy's been buying Snapples for $1.99 each from the corner grocer for years. Recently, the grocer started charging 40 cents for each plastic bag the customer takes. And then Rudy always takes 2 plastic bags. So no matter what, he's going to take 2. And it says, is this proportional? So your explanation would probably be a little more wordy than mine. I'm just going to say, no, it's not proportional. The 2 plastic bags mean the cost does not start at 0. Start at 0, 0. And what I mean by that is if we drew a graph, the cost of the bag would make the graph start right here because no matter what, you're getting that bag. And then go up like that. All right, here, so for letter B, if X represents the number of Snapples the customer is buying and Y is the total cost, write an equation representing the situation. So Y is the total cost. $1.99 for each Snapple. So if we multiply $1.99 times each Snapple, we're going to get the cost for the Snapples. And then we need to factor in the bags. The way I wrote it, it's a little bit unclear because we don't know if every customer always gets 2 bags. I'm going to go ahead and assume in this situation that every customer is like Rudy and always gets 2 plastic bags. So since each bag is 40 cents, together they're always going to get, it's always going to be 80 cents for the bag. So this is the price of the Snapples. And this is the price of the 2 bags. I'm trying to cross that out. All right, letter C. Could Rudy ever be charged $4.32 for Snapples? Why or why not? Well, let's look up here at this problem. We know that Y here was the total cost, and this here would be the total cost. So let's plug it in. $4.32 for Y, and then we have now the rest of it is just an equation, which we know how to solve. And what I'm looking for here, the reason I'm solving this is because I want to see if the number of Snapples I would have to buy is a number that makes sense, right? Like if it's 2, I can buy 2 Snapples, or Rudy can buy 2 Snapples. But is Rudy going to buy 4.38 Snapples? Probably not. Let's see how it works out. So the first thing I'm going to do is I'm going to subtract 0.8 from both sides. So 4.32 minus 0.8, I'm typing in my calculator because I don't want to have to do the work here, is going to come out to 3.52. And now I can actually just divide both sides by $1.99. And that would mean that he would have to buy 1.7688, and it goes on a little more. So we would say no in this case because he can't buy that many Snapples. It's not a whole number. I'll let you write that, but for the sake of brevity, I'm just going to continue going. Here we go for number 9. Rewrite the following expression by combining like terms, making 0 pairs, or using the distributive property. We start with x squared, nothing to do there. Could distribute the 7. So that would give me 7x minus 9 times 7 is 63. That minus 4 is just by himself. Distribute the 5x here. So 5x times 6x actually gives me 30x squared. And 5x plus 1 gives me 5x. Now I'm going to combine like terms. So the 30x squared and the single x squared here makes 31x squared, right? If I have 30 of something and I add 1 more, I have 31 of it. 7x plus 5x will give me 12x, and minus 63 minus another 4 gives me minus 67. And that's as far as I can go. So there you go. There's your Chapter 7 practice test. Good luck.